Hello. So in this presentation, we're going to be looking much more specifically and somewhat in depth into scientific reasoning. And we've seen this show up already. Earlier in chapter 10, they were sort of hinting at, or maybe even explicitly stating some of the things that they were talking about is scientific reasoning, or shows up in science one way or another. And it's been hinted at here and there, sort of sprinkled through the rest of the book. But in this section, that's the main focus, is just sort of what sorts of argument patterns do scientists go through when thinking about their subjects. Just a sort of stage setting as always here. So what scientists are sort of mainly in the business of trying to produce is sort of understanding of nature. That is, they're trying to produce explanations for what is nature made of, what is nature like, how does it work, and so causal explanations about what's going on in nature, why things happen, why they don't happen some other way, how we could change them. These are all sort of causal explanations. So we're getting causal understanding of nature. And of course, they're basing those explanations, those theories and hypotheses that include causal explanations, they're based on evidence, right? Carefully, hopefully, carefully gathered evidence that is in favor, it's supporting these causal explanations. So, I have to be just a little bit careful here because the philosophy of science is my area of expertise, such as it is. So I will be including more than what's in the book. In particular, I'm going to be talking a lot more about a specific philosopher of science, one of the more famous ones. His name is Karl Popper, who was very well known and very influential through the 20th century. And so I'll go beyond the book a little bit here, and I'll try not to just go too far beyond the book because there's just so much that could be said about this topic. Anyway, the two things that really are going to occupy our attention mostly here is, first of all, what form of logic is involved in scientific reasoning? Since this chapter 10 is on induction, it seems pretty obvious that there's going to be some induction involved, right? There's going to be that kind of logic. But one of the big topics that philosophers of science in the 20th century really struggled with and debated over and over again is, to what extent is deductive logic used in science? And Karl Popper, this is what he's most well known for. So we'll see what he has to say about that. So what kind of logic is involved in scientific reasoning, but then also once we have a particular kind of reasoning in front of us, how do we judge the quality of those arguments that scientists are providing, or scientists are sort of going through, what's the quality of their reasoning here? To what extent, like, how do we go about trying to judge whether we should trust what the scientists are concluding? Okay, so first one first, right? What form of logic is involved? Well, a little more stage setting there. So if you were to look at some introductory science textbook, in the first chapter, they might go through like, this is science, and they might provide kind of a systematic scientific method. It might be in the form of a flow chart or something, and there's a good chance it looks something like what we have on this slide here. So if you're going to be a scientist, right, you're going to start conducting some scientific research, you can't just sort of step out into nature and just start understanding it all at once, right? You can't just sort of gather all this information and make sense of it, all together. That's sort of a hopeless enterprise. You need something to focus on, some particular aspect of nature, an interesting phenomenon that draws your attention, or some specific problem that needs to get solved, something to like narrow down the kinds of things that you need to be paying attention to. That might not sound like a scientific thing to be doing, but that is sort of the first step. You got to have a topic, right, that you're actually trying to do research on. Then, just from your past experience, sort of your common sense understanding, or maybe your expertise, your educational background and your experience and so on, you come up with some kind of at least tentative causal explanation for why this is happening, right? Why does this phenomenon happen in nature, or a proposed solution to whatever problem you're trying to solve. And so that's the hypothesis. And then you try to generate some prediction or predictions based on that hypothesis, right? So something that you can test. So given that this hypothesis is true, if the hypothesis is true, what should we expect, right? What sort of predictions come out of that hypothesis? Then you set up some situation, a test, to try to generate that prediction, try to make that prediction happen as best you can and as systematically as you can, and see if the prediction turns out to be true or not. And so that's the evidence that you're gathering from your test. Did the prediction happen as sort of believed it would based on the hypothesis, or did the prediction turn out not to be true? And so then what? And that's really most of what we're going to be looking at from now on, is the then what part of this, because so far this is pretty uncontroversial, right? This seems like basically you look at any professional scientist, this is roughly sort of what they're doing. And then the question about scientific reasoning shows up after that, right? So what after you've gathered this evidence, how does this evidence relate to the hypothesis and logically, right? So if the evidence is included in the premises, to what extent do those premises support the conclusion, where the conclusion is the hypothesis or the causal explanation that you're trying to support? Okay, so it's going to be very useful to have an example in front of us to see how this plays out. And this is a super famous example. It's one that they include in the textbook as well. So this is Ignaz Semmelweis, who was a German doctor, I believe, in the mid-1800s. And so he was an official at a hospital, and he recognized something that was certainly a big problem. So this was something that definitely was focusing his attention. So step one in that method from the previous slide is sort of established here. He was looking at the maternity wards, right? So women were coming into the hospital, staying in the hospital for a couple of days to give birth. And it turns out, well, first of all, the maternity ward in the hospital was separated into two places in the hospital. They called them the two divisions. And there was a difference in the mortality rate, right? The rate of death in the two divisions. In division one, they had this extremely high death rate, right? About 10% of the women who went into the first division died, which is insanely high. And even in the second division, by today's standards, a 2 to 3% mortality rate in a maternity ward is definitely unacceptably high by today's standards. But in the mid-1800s, that was sort of par for the course. You sort of expect that, something like that rate. But it's important to note that even though we might look at this about 10% mortality rate and just say that in and of itself, that is unacceptable, one of the key things here is that there's a difference between the two, right? So it's a problem that this many women are dying, but it's also like, the question is, why is there this difference? What's different about the first division that's causing this higher mortality rate? It's different than the second division. That causal influence seems to be absent. So Semmelweis was in charge of trying to figure this out. So he starts coming up with hypotheses. Hypotheses that we could get evidence to sort of support or undermine those hypotheses. Well, keep in mind, this is the mid-1800s, so they didn't really understand fully exactly how diseases work and how diseases are spread or anything like that, something that could cause this sort of death. And that's what it was. I mean, they at least knew that there's a disease here. The women, they called it childbed fever, right? So the women were getting a fever, so they're having these specific symptoms, what we today recognize as sort of an infectious disease symptom. And so that's sort of where Semmelweis started. They understood at least this basic idea that diseases can be spread through the air. So he thought, well, maybe there's some airborne contagion. And that's what's getting the women sick and killing them. Well, okay, but this doesn't explain why there's a difference between the two divisions. If this is a general airborne contagion, then we should expect it to be infecting sort of the two divisions equally. But clearly in the first division, there's a much higher mortality rate. So this hypothesis of general airborne contagion didn't seem to be compatible with the fact that there's a difference between the two divisions. So set that aside. That seems like evidence against the hypothesis. Then he thought about this one, right? It was also known that crowding can lead to greater disease outbreaks, right? So in the more densely populated areas, you tend to get more diseases showing up. When people are sort of spread apart from each other, you don't see that kind of thing. So maybe that, right? Well, the evidence was pretty straightforward there, especially once it became known that the first division has a much higher mortality rate than the second division. Most of the incoming mothers that were about to give birth wanted to get into the second division. So this set into the first division. Yeah, the second division, the one, here we go, the one that had the lower mortality rate, that's where the women wanted to get into. So it turns out that the second division was actually more crowded. So if overcrowding is causing the disease, then you would expect the second division to be worse off, but that wasn't the case. So it doesn't seem like the overcrowding hypothesis is really working out. So here's another one. He noticed this difference, that in the first division, the one with the higher mortality rate, the women were being treated by the male medical students, whereas in the second division, the mothers giving birth were attended to by the female midwives of the hospital. So this seems like a pretty big difference. So Semmelweis hypothesized that maybe it's the rough treatment of the male medical students. Keep in mind, this mid-1800s, gender stereotypes were very strong, alive and well back then. And so the idea that women were sort of so fragile somehow, that like these overly aggressive males, they're so strong that they would be harming these women to such a degree that they were dying in much higher rates than the ones who were being treated by the female midwives. Well, I don't know if any of you have gone through the birthing process yourselves, right, have given birth, but I hear that it's a fairly rough process. So it just seems kind of implausible that the male medical students were so rough that it was so much more rough than just the birthing process on its own, that the male medical students' treatment was responsible for such a higher mortality rate in the first division. So again, sort of set that aside. Okay. Well, here's another sort of interesting hypothesis that, well, in the hospital, there was always whenever anybody was dying anywhere in the hospital, not just in the maternity ward, when somebody was about to die, they would do the last rites ritual. The last rites ritual involved a little procession that would go through the hospital that was led by a priest, because this is a religious ceremony. And they would be ringing this bell that was like the death bell. And so whenever you saw this procession going by, you knew somebody in the hospital was about to die. Well, it turns out that this procession went near enough to the second division that the women there could see the procession going by and hear this bell ringing, whereas in the second division, the procession did not go by, so the people there didn't hear it. So Semmelweis thought, well, maybe this is so disruptive, right? It's so unsettling and so disturbing to the women in the first division that it's actually, I don't know, almost scaring them to death, right? Again, gender stereotypes, you know, these fragile women are just getting overwhelmed by fear and they end up dying as a result. So anyway, you know, this seems like a pretty easy thing to test. You just reroute the funeral procession, right? The last rites procession, so it doesn't go past either maternity ward, and see if the death rate in the first maternity ward goes down. Well, predictably it did not. And so that seems to indicate that that hypothesis is incorrect either. Okay, oh, another one, birthing position. You saw that this was a difference. So in the first division, the women were giving birth on their back. Whereas in the second division, they were giving birth while lying on their side. Remember, the death rate was higher in the first division. So maybe, Semmelweis thought, maybe giving birth while lying on your back causes a higher mortality rate. So he ordered the people in the first division to have women also give birth while lying on their side. I never knew that was a thing until I read about the Semmelweis story here. But as you could maybe predict, that had no effect either. So this birthing position hypothesis did not seem to be supported by the evidence. And so at this point, Semmelweis had kind of run through all of his proposed hypotheses that he could come up with until one day he was working with a colleague in the morgue, right, doing an autopsy. And so that involves using a scalpel to cut through dead tissue. And during that process, his colleague accidentally cut his own finger, which you would think, not a big deal, they didn't think, until days later, he started to develop the exact same symptoms that the women in the first division of the maternity ward were developing. And in fact, this doctor actually died as a result of that. And so Semmelweis saw this play out. It's like, wow, that's just too similar to what's happening to the women. So he did another review of procedures in the hospital. Yeah, so he noticed that those male medical students who were attending to the birthing mothers in the first division of the maternity ward, he noticed that those male medical students, well, they do this thing that all medical students do. They go on rotation through the hospital, so they get a sense of sort of all the different jobs that are going on, the medical jobs that are going on in the hospital. And he noticed that their schedule had them attending and helping out with autopsies just before they go into the maternity ward and help out with births. And like I said, mid-1800s, didn't understand sort of infectious disease spreading very well. And so the doctors would attend to autopsies, then just sort of, like wipe their hands off a little bit and then go right into the maternity ward. And of course, the birthing process could involve some tearing tissue, and then the medical students have their hands right down in there. And so the thought is maybe they're introducing this, what Semmelweis called cadaveric material, right? Material from cadavers, from dead bodies, was being introduced into these women's bodies, and that was causing the problem. Well, so what do? Well, you wash your hands. Back then, they didn't realize that washing your hands was so critical to preventing the spread of diseases like this. So Semmelweis ordered people to start doing it, and lo and behold, it actually helped a lot. In fact, the mortality rate in the first division dropped to below the rate in the second division, right? The second division was the good division, but now the first division's doing even better just because of hand washing. So this is sort of a standard process of science that they talk about in chapter 10 in the book, that you remove what you suspect is the causal influence for some effect and see if the effect is still there. Well, Semmelweis removed the causal influence by asking people to wash their hands, and the effect disappeared. All right, so this is a pretty good hint that this hypothesis about the cadaveric material is on the right track. Well, just to make sure, he tries this other technique that's also described in the book, that you intentionally introduce the causal factor and see if you can reproduce the effect. Well, Semmelweis ended up intentionally introducing this dead tissue, this cadaveric material, into the bodies of 12 otherwise healthy women, and 11 of them died. So we introduced the suspected causal influence, and the phenomenon shows back up again. So this gives us some pretty good evidence. When we intentionally take the causal influence away, the phenomenon goes away. When we intentionally bring the causal influence back in, the phenomenon shows up again. That's really good science. Unfortunately, it's also, in this case, terrible ethics, right? I mean, he basically murdered 11 women in order to establish with really high confidence that this is the correct hypothesis. It was the dead tissue that was causing the problem all along. Now, it did lead to a dramatic drop in mortality, and just to kind of fill out the story, people were so resistant to this idea, right? It takes a long time for people to change their mindset on things like this. So this whole hand washing business actually didn't catch on really until after Semmelweis was already dead. So he didn't get the recognition he deserved during his time, during his lifetime. Okay, moving on. So now let's look at sort of the logic that's involved with this story. And we're going to use some symbols that are standard symbols that are used by philosophers of science that work in this area. So logically enough, they use capital H to represent the hypothesis. So that's the thing we're actually trying to test. We're trying to get support for this. And then they use capital letter I. This is a little bit unfortunate. It'd be nice if they used maybe a capital P for the prediction based on the hypothesis, but capital P gets used for lots of other things, and so they didn't want to use it again here. So instead, they call this the test implication. That is basically just the prediction that's based on the hypothesis. And this is the, the symbols that have come to be used most often, so we got to stick with it, right? So hypothesis, H, and then I is the test implication. And so the thought is that if the hypothesis is true, then the test implication should be observed, right? So once you set up the test, we've got a predicted result of that test. That's the test implication. So then for the rejected hypotheses, things like birthing position and the scary priest procession walking by and those sorts of things, this seems to be the argument pattern, right? If the hypothesis is true, then the test implication should be true. The test implication is not true, so therefore the hypothesis is not true. Keen-eyed observers might recognize that this is the modus tollens argument form that we've seen a few times, especially in chapter 1. And we know that this argument form is deductively valid. So, looks great, right? We've got a deductively valid style of reasoning here for rejecting a hypothesis. Sounds good. Right? All right, so that's fine, but what about for the successful one, right? That the dirty hands hypothesis, the one that turned out, it seems to be sort of do the trick, right, to solve the problem. Well, here's the pattern of reasoning there. If the hypothesis is true, then the test implication should be true. The test implication was true, so therefore the hypothesis is true. That sounds like what's happening, right? We've got this evidence, showed our hypothesis is true, so we're good to go. Like, well, there's a problem. And again, keen-eyed observers might recognize what this problem is. This is the fallacy of affirming the consequent. It turns out that this is following a deductively invalid argument form. So this does not prove that the hypothesis is true, right? A deductively invalid argument cannot prove things like that. It cannot give us sort of 100% absolute guarantee that this conclusion is true. But we do have sort of evidence in favor, it seems, evidence in favor of this hypothesis. So it seems like we've got inductive support, right? These premises here seem to be supporting the conclusion, just not supporting it 100%. So maybe that's good enough. But over the years, this fact, right, that this style of argument does not prove the conclusion 100% for sure guaranteed to be true, this is referred to as the problem of induction. And ultimately the problem of induction is just, it's not deduction, right? No finite amount of evidence, empirical evidence as we call it here, evidence gathered through these scientific techniques, can conclusively prove that a hypothesis is true. And if you really sort of press professional scientists on this point, they will hopefully always acknowledge that, yes, like we've got lots of evidence in favor of our conclusions, but yeah, who knows, maybe some new information will come to light in the future that will cause us to change our mind. And so they'll admit that they haven't proven absolutely guaranteed 100% that their conclusions are true. And so, yeah, induction is just not deduction. That's kind of all that the problem of induction is trying to say. But this seems okay, right? The hypothesis, given that evidence, right, that, in the Semmelweis example, when you wash your hands, that seems to make the problem go away. And so this seems to make the hypothesis more likely to be true, or we might say that our confidence in the truth of the hypothesis has gone up by a lot. When we see this evidence come in. But we need to recognize that the problem of induction still applies here. So we wouldn't be able to say that it's conclusively proven that the hypothesis is more likely to be true. It's sort of a weird conclusion anyway, to say it's 100% guaranteed that the hypothesis is more likely to be true, or it's 100% guaranteed that our confidence in the hypothesis went up. Sort of, it's a weird conclusion. And what's weird about it is that you can't have a deductively sound argument that shows you exactly how much more confidence you should have. How much more likely is this hypothesis to be true? There's always a little bit of what we might call kind of intuition, even if it's kind of expert intuition that's involved with figuring out exactly how much support a given bit of evidence is providing for a hypothesis. And then also, there's this. If we're saying that, you know, for the Semmelweis example, that hand washing, right, that's going to solve the problem. We figured it out. This hypothesis is the correct one. And so from now on, everybody should wash their hands in order to avoid this problem of infection. Well, that assumes that the causal situation that we figured out today is going to be the same tomorrow, and the same a month from now, a year from now, a decade from now, or indefinitely into the future. So there's this sort of subtle, unstated premise in that reasoning that the future will resemble the present and the past. But if we're talking a deductively sound argument, right, the highest possible standard of proof for that kind of a conclusion, we have to recognize that that's one of the premises, that the future will resemble the past. And we just don't have conclusive evidence, right? We don't have a conclusive argument. We don't have a deductively sound argument that that's true. And this harkens back to the bit about external world skepticism, where we cannot even conclusively 100% guarantee that there even is an external world, right? And so if we can't even conclusively prove that, then we can't conclusively prove that whatever the future is, it's going to resemble whatever this present is. So, you know, if we're going to be really hardcore about it and hold our beliefs to this highest possible standard of requiring a deductively sound argument to establish our beliefs, then this belief that the future will resemble the past, we just don't have a deductively sound argument for that. We have to admit it. So even though this might sound really plausible, you know, the hypothesis is more likely to be true, even that kind of a conclusion, if we're being sort of like correct, technically precise about things, we still don't have a deductively sound argument in favor of that. So that's where Karl Popper finally comes into the picture. So like I said, he was a very well-known philosopher of science, very influential philosopher of science, who was active, like by the 1940s up through the 1970s, was sort of his main time of influence. And definitely beyond that, sort of when he was alive and doing his most work was during that mid-20th century time period. And so he was picking up on this problem of induction and trying to show that not only is induction not deduction, which we already knew, but that it actually produces bad science when we're relying on induction. That's what Popper is famous for. And even if you've never really heard of Karl Popper before, you've probably heard of some of his ideas before. I have something down here in the fine print at the bottom. That's sort of what we might call like a bumper sticker version of Popper's ideas. So 1,000 successful experiments can never prove the theory true, but one unsuccessful experiment can prove a theory false. Maybe you've heard something like that before. And that's roughly capturing what Karl Popper's interested in. And to show us what the problem is with using induction in science, he uses these case studies. So Freudian psychology is one of his main targets here. And that's what I'll focus on. But he also had this version of historical study that was popular, especially in the early to mid 20th century, sort of this Marxist approach to history. This was being presented as finally this scientific approach to history. And rather than science or history just being sort of storytelling and guesswork, no, now we've got like this scientific theory and a scientific method for converting this historical research into science. And same thing with psychology, finally with Freudian theory, and this other guy, Adler, certainly didn't have as lasting of a presence in sort of popular awareness as Freud, but nevertheless, he was a popular theorist at the time. But the idea was that psychology is turning into this science. And keep in mind, you know, back especially in the early 20th century, it was pretty shaky science. So what were they doing, right? What are the Freudians doing? Let's look at them first. So, all right, here we are. We're Freudian scientists. So let's go about looking for evidence that's related to our theory. So they're looking at examples of human behavior because it's psychology, so that's the evidence, is all the human behavior. Lo and behold, all the examples of human behavior that they saw seem to be supportive of their theory. You know, their theory was readily able to explain all of these examples of human behavior. So it looks like they're on the right track. So it's successful over and over again. In fact, it was never unsuccessful. No evidence against a theory was ever observed, right? No examples of human behavior were ever observed that sort of seemed to defy Freudian theory. So, you know, maybe this means that Freudian theory is like a really good theory, right? It's very much on the right track. But there's some problems here. One of the problems, I'm going to go backwards here. One of the problems is that Freudian theory and Adlerian theories were directly opposed. They were absolutely incompatible with each other. So it's just impossible. Even the psychologists themselves recognize that it's impossible for both of these theories to be true. However, both of them were having this level of success. Both of them were able to show that all examples of human behavior are supportive of their theory. So then what about this? Like somebody would say like, okay, so now I'm going to try to trip them up. I'm going to come up with an imaginary example of human behavior. And I'm going to construct this imaginary example in such a way to try to make it count against the theory. Like if we were to really see this imaginary example of human behavior really happening, then that would count against their theory. Well, it turns out that it's impossible to come up with such an example. No matter how crazy and weird and twisted of an example of human behavior people would present every single time, it seemed like even that example would count in favor of their theory. This is similar to what is sometimes called confirmation bias, right? If you are sort of convinced that your belief is true, then when you start looking out into the world, you'll only notice the things that are supportive of your theory. In fact, even things that would seem to count against your theory, you might reinterpret them or slightly modify your belief in such a way that it turns out that this new bit of information, this new bit of evidence actually does support your belief. And that seems like what's going on here. That it just seemed to be impossible for any evidence, real evidence, or even imaginary evidence to count against their theory. And that seems like these are bad scientific theories, right? And so Popper coined this term. These theories are unfalsifiable. That is, they do not tell us what should not happen, right? They might give all these predictions about what should happen in human behavior, but they don't tell us anything about what should not happen. And this is radically different from many theories that Popper and sort of the scientific community at large would recognize are good scientific theories. Say like something simple like a Newtonian theory of gravity, right? So according to the Newtonian theory of gravity, if I let go of this pen, what should happen? Right? It's got a positive prediction about what should happen to this pen. It should fall. But equally importantly, the Newtonian theory of gravity also says what should not happen. It says that if I let go of this pen, the pen should not just sort of like drift away or start like bouncing around the room or something. So that if here I am on Earth, you know, I'm not in orbit, I'm not an astronaut, I'm not out in space or anything, I'm just sitting here on Earth. If I let go of this pen and the pen just floats away, that would seem like it would, something weird's going on, right? That is counter to what Newtonian theory says. So a good scientific theory should tell us what should happen, but it should also tell us what should not happen. And that's not what these psychological theories were doing. So it seems like these theories, although they had some sciencey elements to them, if you look down in the details, they just didn't have enough substance to be considered real scientific theories. So as Popper perhaps accurately labels them, these are pseudosciences, at least at the time, right? In the early to mid 20th century, psychology was a very young field of research, and so it really hadn't achieved scientific status yet. And certainly the old Freudian theory itself was a pseudoscience. So sort of driving the point home, a good scientific theory should tell us what should not happen. And so further, Popper's take-home message here is that the problem was in using induction, right? Since these scientists were like, had this theory, or the supposed scientists anyway, they had their psychological theory. They're like, okay, let's start doing science. And so they thought doing science is finding evidence in support of your theory, induction. And so they're doing this inductive process of scrambling around trying to find all this evidence in favor of their theory, and that drove them away from being good scientists and having a good scientific theory. So Popper says induction is to blame. When you're trying to use induction to support your theories, you're inevitably, Popper thought, going to drift off towards pseudoscience. So you should avoid ever using induction in this way if you're doing science. If you're not interested in doing science, fine, but if you're going to do science, avoid using induction in this way. And so there is just no deductively valid procedure to prove a general statement true. We know that already. That's the basic problem of induction. But the other thing we know is that there is a deductively valid procedure to prove a hypothesis, or general statement, as he sometimes called them, to prove something like that false. And of course, that's modus tollens. Now, modus tollens applied to science in this way has come to be called Karl Popper's method of falsificationism, right? We're trying to prove that these hypotheses or these scientific theories are false. So we've seen this already. If the hypothesis is true, then the test implication will be observed. The test implication is not observed, so therefore the hypothesis is false. This is what scientists should be trying to do, says Popper. And by the way, just sort of as an aside here, why am I spending so much time talking about Karl Popper? Well, for one thing, clearly what he's talking about meshes really neatly with this class. He's talking about specific elements of logic, specific deductively valid argument forms, and deductively invalid formal fallacies, like the fallacy of affirming the consequent. And so after taking this class, you're sort of very well primed for understanding what Popper was talking about. So in that case, it's sort of a good example of how the stuff we're learning in the class links up with sort of philosophy in general. The other thing is that if you talk to professional scientists, many of them will actually claim to be Popperians, right? They will claim to be following Popper's method of science, Popper's falsificationism. And especially if they get into some kind of dispute, some debate with some other research group, they might, as part of their reasons for supporting their side of the debate, they might accuse the other research group of not following Popper's method of falsificationism. And so that's used as a reason for disbelieving this rival research group. Well, what I'm going to end up showing you here is why that's sort of not very good argumentation. Scientists should stop saying that, because it turns out that Popper's method of falsificationism doesn't work very well. And people who have taken this class on logic are very well set up for understanding why Popper's method just doesn't work that well. In fact, it probably doesn't work at all. It shouldn't be sort of the scientific method. All right, so Popper wants to show us that scientists should always be just proving things wrong, right? That's the method of science that all scientists should be in the business of pursuing. So to convince us of that, he gives us this example, a really famous example from the history of science that everybody, that all the scientific community and the philosophers and so on, will all recognize as a good example of science in action. So it was the switch, or sort of the test between the old Newtonian theory that had been around for centuries versus this new theory in the early 20th century coming from Albert Einstein, his theory of general relativity. So according to the Newtonian theory, light, when it's traveling through empty space, will always go in a straight line. Now, if the light encounters an object, the light might just be absorbed by that object, or it might reflect off of that object. Or if the object is transparent or semi-transparent, the light might go through the object, but get refracted, right? So when, for example, light goes from air to water, the light bends, it gets refracted. So that could happen. But if there's no material, right? It's not traveling, hitting an object or traveling through any material at all. It's just through empty space. Of According to Newton, light always goes straight. But according to Einstein, if light that's traveling through a vacuum, right, it's traveling through completely empty space, if that light is traveling through a strong gravitational field, the path of the light will indeed get bent. What are the reasons for that? Well, those are complicated that we don't need to get into, but that's the different prediction that Einstein has. So this is very difficult to test, right? You'd have to set up a strong gravitational field in your laboratory and see if light bends as it gets near this gravitational field. It just can't be done in a lab. So you have to look out into the heavens for massive objects that have strong gravitational fields and look at light that's passing by those objects to see if the light bends. The moon isn't quite big enough, it's not massive enough to have a strong enough gravitational field to bend the light enough to create this effect in a measurable way, but the sun is. The sun's plenty big enough to create a measurable effect. The problem, of course, is that the sun itself is extremely bright, so it makes it difficult to see any other light sources, which is the stars, starlight, to see if that light is bending as it gets near the sun. So they had to wait for a full solar eclipse. Einstein proposed this theory in 1915, and then in 1919, some people went out to areas around the world where there was going to be a full solar eclipse visible, and then tried to see, once you could see the stars, once the moon blocks the sunlight, you can see the stars and see if that starlight was bending or not. So here's the basic setup, right? So here we are on the Earth, down here in the bottom right. Then there's all these stars out in the sky, and astronomers have spent really thousands of years cataloging the precise position of all of these different stars. And so they have these catalogs of thousands and thousands of individual stars and their exact location in the night sky from our perspective. So what the astronomers did was, they don't show the moon here, but assume the moon is blocking this light from the sun. They looked for a star where they knew where the actual position of the star is according to their catalogs. And then if it turns out that that very star is observed to be in a different place in the sky, then the only explanation for that is that the light from that star bent. It changed direction as it went past the sun. And so this is sort of what it would look like here, right? Here's the star, the beam of light coming from that star. It goes through the strong gravitational field of the sun and bends, and then it comes to us. And so from our perspective, as we're looking back out at this ray of light coming in at us, we follow it out and it looks like the star is right here, when in fact, it's off to the left over here. And so that's what they were looking for. So let's be a little more precise about it. What's the test implications? According to Newton, the test implication is the light will go straight, or put in the negative to satisfy Popper, the light will not bend. Whereas Einstein said the light will bend, that is, the light will not go straight. So maybe you can guess what happened. The light bent. This is an actual photograph that Eddington, one of the astronomers involved, took this picture. You can just barely see some markings that he made here on the photograph showing the displacement, the apparent displacement in the sky of some known stars. And so the explanation was that the light from that star, those stars, was being bent as it came to us through the strong gravitational field of the sun. This is a headline in the New York Times saying, like, Einstein wins, this crazy theory turns out to be true. Or at least that Newton is false, right? So here's the falsificationism, right, in action. Newton said that if Newtonian theory is true, then the light will go straight. The light did not go straight. Therefore, Newtonian theory is false, deductively valid. Okay, so it seems like we've proven that Newtonian theory is false. And so, you know, some people might say, well, Newtonian theory has been around for so long, maybe we don't want this one result to sort of negate this whole theory that's been really great for us for so long. Well, Popper says that's just sort of sentimentality, right? Once the negative evidence is in, then scientific reasoning demands that you reject the hypothesis. That's modus tollens. You've proven that the hypothesis is false. So any sort of attachment to that hypothesis, if you insist that it's not false, that's irrational. You're just being emotional about sort of your favorite theory that you don't want to give up. And any attempts to sort of explain away this evidence that seems to prove this theory false these attempts to explain it away are, as we call it, an ad hoc attempt to explain away the evidence. So an ad hoc explanation, maybe you've seen that sort of a thing before, but this is something that is suggested so people want to save their favorite theory in the face of this negative evidence. So they come up with this sort of brand new consideration, or this brand new explanation to try to show that we should not reject this hypothesis or this theory, even though we just seem to get some really good evidence against it. My favorite example of this involves Galileo. So you might know Galileo was one of the first people to use a telescope. In fact, he's sort of the first person we know of to use a telescope to look up at the heavens. And at the time of Galileo, so famously, he was sort of fighting against this old idea of the structure of the universe, where the Earth was at the center of everything. But one of the other aspects of this old theory, in addition to the Earth being the center, was that everything outside the Earth, the sun, the moon, the stars, and their orbits and everything, or their pathway through the sky, it's all perfect circles or perfect spheres in the case of these objects. So all these celestial objects, including the moon, were perfect spheres. Now the moon is sort of splotchy that we could see, but according to this old Aristotelian theory, the moon itself is a perfectly smooth sphere. Well, Galileo used his telescope to look at the moon over the course of many months. He noticed, this is actually one of his drawings, he noticed these shadows on the moon. Now, he didn't recognize that these were impact craters. He thought these were weird valleys and mountains and so on. But he saw these shadows, and he saw that as the angle between the moon and the sun changed over the course of a month, these shadows would shift. And so this indicates that the moon has texture to it, right? So if the moon's surface has this lumpy texture, then that means that the moon is not a perfect sphere. And so it seems like we've falsified the old Aristotelian theory. According to the old Aristotelian theory, the moon is a perfect sphere. Turns out the moon is not a perfect sphere, so therefore the old Aristotelian theory is false. Well, the Aristotelians had an ad hoc response to that. They claimed that there was this invisible substance that fills in the imperfections on the moon so that it does smooth everything out, so that although you can't see this invisible substance because it's invisible, but it does indeed smooth out the moon into a perfect sphere. Done and done, right? Explains away Galileo's evidence. Well, nobody had ever proposed that there's an invisible substance on the moon before. Clearly, they're only bringing this up to save their favorite theory in the face of this pretty powerful evidence against their theory that Galileo had provided. So this is a classic ad hoc explanation. All right, so I'll mention this then. That Galileo did have a response here. You know, he's sort of making fun of the Aristotelians with this response. You know, maybe the invisible substance, says Galileo. It's like, oh, I forgot about the invisible substance. You guys are right. I should have taken that into account. But it turns out that the invisible substance actually makes the moon more lumpy. It doesn't smooth things out at all. The substance is even lumpier than what you can see. And so the moon is definitely not a perfect sphere. Okay, so how do we sort between these two ideas of the invisible substance here? Clearly it's impossible, and so the Aristotelians were sort of backed into a corner by Galileo's response. All right, so moving on in Popper's ideas. Sometimes, of course, attempts to falsify a theory don't work out, right? You try to show that the theory or the hypothesis is false, but the evidence comes back as predicted by the hypothesis. And so you don't get to run through your modus tollens falsification procedure and prove that the hypothesis is false. So what are we to conclude from this? Well, remember, Popper didn't want to use induction at all. And so any claims that the hypothesis is true, or that the hypothesis is more likely to be true, or that we have more confidence in the hypothesis, that's all inductive reasoning. And according to Popper, should not be done in science. All Popper really wants to say then is that the hypothesis has been borne out, not that it's more likely to be true, certainly not that it is true. So what it turns out is that really there's only two kinds of hypotheses, according to Popper: those that have already been falsified and those that have yet to be falsified, right? There's no room for true hypotheses or more likely to be true hypotheses or anything like that. Really, these are the only two, according to his very strict account of science. Okay, so that's been going on for a while now. So I'll go ahead and pause it here and then pick up the story in the next presentation.